Python was created by Guido van Rossum and first released in 1991. Guido started working on Python in December 1989 as a hobby project during his Christmas break while working at the Centrum Wiskunde and Informatica in the Netherlands. He wanted to create a successor to the ABC programming language that would appeal to Unix and C hackers. What's fascinating is that Guido didn't expect Python to become as popular as it did. He simply wanted to fix some issues he saw in existing languages and make programming more enjoyable. The name Python itself has an interesting origin that many people get wrong. It wasn't named after the snake at all. The language is actually named after the British comedy group Monty Python's Flying Circus. Guido van Rossum was a big fan of the show and wanted a name that was short, unique, and slightly mysterious. He was reading scripts from the show while implementing Python and thought the name would be perfect. This playful origin reflects Python's philosophy of making programming fun and not taking itself too seriously. The official documentation even contains references to spam and eggs, which are nods to famous Monty Python sketches. This whimsical naming convention has become part of Python's culture, where terms like spam and eggs are commonly used in example code instead of the traditional foo and bar you might see in other programming languages. Python is an interpreted language, which means your code is executed line by an interpreter rather than being compiled into machine code beforehand. When you run a Python program, the Python interpreter reads your source code and converts it into bytecode, which is then executed by the Python virtual machine. This is different from compiled languages like C or C++, where your entire program is converted to machine code before it runs. The interpreted nature of Python makes it incredibly easy to test code quickly. You can open a Python interactive shell and immediately start typing commands and seeing results. This rapid feedback loop is one reason Python is so popular for beginners and for prototyping. However, this convenience does come with a trade-off in execution speed compared to compiled languages. Python uses dynamic typing, which means you don't have to declare the type of a variable when you create it. In languages like Java or C, you have to explicitly state whether a variable is an integer, string, or some other type. In Python, you simply assign a value and Python figures out the type automatically. You can write x equals 10 and Python knows x is an integer. Later, you can reassign x to be a string like x equals hello, and Python handles it without complaint. This flexibility makes Python code more concise and easier to write, especially for beginners. The interpreter keeps track of types at runtime, checking whether operations make sense for the types involved. While this adds some overhead, it significantly reduces the amount of boilerplate code you need to write. Indentation is not just a style choice in Python. It's actually part of the syntax. Unlike languages that use curly braces or keywords like begin and end to define code blocks, Python uses indentation levels. If you have an if statement or a for loop, the code inside that block must be indented consistently. This forced indentation makes Python code remarkably readable because you can't write messy, poorly formatted code that still runs. Many programmers initially resist this when coming from other languages, but most eventually appreciate how it enforces clean, readable code. The standard is to use 4 spaces for each indentation level, though technically you can use any consistent amount of whitespace. Mixing tabs and spaces, however, will cause errors in Python 3, which helps prevent a common source of hard-to-debug issues. Python follows a design philosophy outlined in the Zen of Python, a collection of 19 guiding principles written by Tim Peters. You can actually view these principles by typing import this in any Python interpreter. Some of the most famous principles include beautiful is better than ugly, explicit is better than implicit, simple is better than complex, and readability counts. There's also the principle that there should be one and preferably only one obvious way to do it, which is sometimes called the Pythonic way. These aren't just abstract ideals. They actively influence how Python is developed and how the community writes code. When experienced Python programmers say code is Pythonic, they mean it follows these principles and uses the language's features in the way they were intended to be used. Python has a comprehensive standard library that's often described with the phrase batteries included. This means that Python comes with a huge collection of modules right out of the box, without needing to install anything extra. Want to work with JSON data? There's a JSON module. Need to make HTTP requests? The Erlib module has you covered. Want to work with dates and times? The datetime module is ready to go. This extensive standard library is one of Python's greatest strengths because it means you can accomplish a lot without having to hunt down and install third-party packages. For many common programming tasks, the tools you need are already there waiting for you. This makes Python particularly good for scripting and automation tasks where you need to get something done quickly without spending time on setup and configuration. Every value in Python is an object, making Python a fully object-oriented language. This might sound abstract, but it has practical implications for how you work with a language. Even simple things like integers, strings, and functions are objects with their own attributes and methods. When you create the number 5, you're actually creating an integer object. That object has methods you can call, like x.bit_length, which tells you how many bits are needed to represent that number. Strings have methods like upper, lower, and split. Even functions are objects that can be passed around as arguments to other functions. This consistent object model makes Python very flexible and powerful. You can treat everything uniformly, which simplifies many programming tasks and enables powerful techniques like decorators and higher-order functions. Python supports multiple programming paradigms, meaning you can write code in different styles depending on what makes sense for your problem. You can write procedural code with functions and basic control flow, which is great for scripts and simple programs. You can write object-oriented code with classes and inheritance when you need to model complex systems with related entities. You can write functional code using features like list comprehensions, lambda functions, and higher-order functions when you want to transform data without side effects. Most real-world Python programs use a mixture of these paradigms, taking advantage of whichever approach works best for each particular situation. This flexibility means you're not locked into one way of thinking about problems, and you can choose the most appropriate tool for each task. Python has become one of the most popular programming languages in the world, consistently ranking in the top 3 in most surveys and indexes. As of recent years, it's often number 1 or 2 on indexes like TIOBA and the PayPal Popularity of Programming Language Index. This popularity isn't just hype. Python is widely used in web development with frameworks like Django and Flask, in data science and machine learning with libraries like NumPy, Pandas, and TensorFlow, in scientific computing, in automation and scripting, in education as a first programming language, and in many other domains. Major companies like Google, Netflix, Instagram, Spotify, and Dropbox use Python extensively in their technology stacks. The language's versatility, readability, and extensive ecosystem of libraries make it suitable for everything from small scripts to large-scale applications serving millions of users. Python has several built-in data types for representing numbers, and understanding them is crucial for writing effective code. The 2 most common numeric types are integers and floating-point numbers. Integers, or ints, represent whole numbers without decimal points, like 5, -42, or 1 million. Python 3 integers have unlimited precision, which means they can be as large as your computer's memory allows. You can literally work with numbers that are thousands of digits long without any special libraries. Floating-point numbers, or floats, represent numbers with decimal points, like 3.14, -0.5, or 2.0. They're implemented using the computer's native double precision format, which gives you about 15 to 17 decimal digits of precision. Understanding when to use ints versus floats matters, because floats can have rounding errors due to how computers represent decimal numbers in binary. Strings in Python are sequences of characters used to represent text, and they're incredibly versatile. You can create strings using single quotes, double quotes, or triple quotes. Single and double quotes work identically, so you can write hello or hello, and they're the same thing. The flexibility of having both types of quotes is useful when your string contains quotes inside it. If your string contains an apostrophe, you can use double quotes around it without needing escape characters. Triple quotes, either 3 single quotes or 3 double quotes, allow you to create multi-line strings that span multiple lines of code. Strings in Python are immutable, which means once you create a string, you can't change individual characters in it. If you want to modify a string, you actually create a new string. This immutability might seem limiting at first, but makes strings safer to use and allows Python to optimize memory usage by reusing identical string objects. Python strings come with a rich set of methods that make text manipulation straightforward. You can convert strings to uppercase or lowercase with the upper and lower methods. You can check if a string starts or ends with certain characters using starts with and ends with. The split method breaks a string into a list of substrings based on a delimiter, which is incredibly useful for parsing text data. The join method does the opposite, combining a list of strings into a single string with a separator between elements. You can strip white space from the beginning and end of strings with strip, or just from one side with strip and restrip. The replace method lets you substitute one substring for another throughout the entire string. These methods make Python excellent for text processing tasks, from cleaning data to generating reports to parsing log files. Booleans in Python represent truth values and are written as true and false, with capital first letters. These are the only 2 Boolean values in Python, though many other values can be evaluated in a Boolean context. When you use values in conditions, like in an if statement, Python converts them to true or false. Numbers evaluate to false if they're 0 and true otherwise. Empty collections like empty lists, empty strings, and empty dictionaries evaluate to false, while non-empty ones evaluate to true. The special value, none, also evaluates to false. This concept of truthiness and falsiness makes Python code very concise. Instead of writing if length of my list is greater than 0, you can just write if my list, and it means the same thing. Understanding truthiness helps you write more Pythonic code that experienced Python programmers will recognize and appreciate. The none value in Python is special and represents the absence of a value. It's similar to null in other languages, but it's actually a singleton object, meaning there's only one none object in your entire Python program. When a function doesn't explicitly return a value, it actually returns none. You can use none to initialize variables when you don't have a meaningful value yet, or to represent optional parameters in functions. It's important to check for none using the as operator rather than the equality operator. You should write if x is none rather than if x equals none. The reason is that it checks for object identity, asking whether 2 variables refer to the exact same object in memory, while equals checks for value equality, which could potentially be overridden for custom objects. Since none is a singleton, checking with is more precise and is the Pythonic way to do it. Python's type conversion functions let you convert between different data types explicitly. The int function converts values to integers, truncating any decimal portion if you pass it a float. The float function converts values to floating point numbers. The street function converts almost anything to its string representation. The bool function converts values to Boolean, following the truthiness rules we discussed. These conversions are essential when working with user input, since input from users typically comes as strings that you need to convert to numbers or other types before you can work with them mathematically. You'll often see code that reads a number from input and immediately converts it with int or float. Understanding type conversion helps you avoid common errors and write more robust code that handles data from various sources correctly. Python uses automatic memory management with a garbage collector, which means you don't have to manually allocate and free memory like you do in C or C++. When you create objects, Python automatically allocates memory for them. When objects are no longer needed, Python's garbage collector automatically reclaims that memory. The primary mechanism Python uses is reference counting. Every object keeps track of how many references point to it. When the reference count drops to 0, meaning nothing in your program can access that object anymore, Python immediately reclaims the memory. Python also has a cycle detector that finds and cleans up circular references, which are situations where objects reference each other in a loop, but nothing else references them. This automatic memory management makes Python much easier to use and less error-prone than languages, where you manage memory manually. though it does add some overhead. Variable names in Python have rules and conventions that are important to understand. Names must start with a letter or underscore, and can contain letters, numbers, and underscores. They're case-sensitive, so my variable and my variable are different variables. Python convention, outlined in PEP 8, which is the official style guide, says you should use lowercase letters with underscores for variable names, like my underscore variable or user underscore count. This is called snake case. Constants, which are variables you don't intend to change, should be in all uppercase with underscores, like max underscore size or default underscore color. Class names should use capwords convention, also called Pascal case, where each word starts with a capital letter, like my class or user account. Following these naming conventions makes your code immediately recognizable to other Python programmers and helps everyone understand what different names represent. Python has reserved keywords that you cannot use as variable names because they have special meanings in the language. Words like if, else, for, while, def, class, return, and import are all keywords. There are currently 35 keywords in Python 3, and trying to use any of them as a variable name will cause a syntax error. You can see the complete list by importing the keyword module and accessing keyword.qlist. It's worth familiarizing yourself with these keywords as you learn Python because they form the core syntax of the language. Sometimes beginners accidentally try to use intuitive names like class or type or list as variable names and are confused by the errors they get. Being aware of keywords helps you avoid these issues and choose better variable names that don't conflict with the language itself. Multiple assignment is a powerful feature in Python that lets you assign values to multiple variables in a single line. You can write x, y equals 5, 10, and Python will assign 5 to x and 10 to y. This is actually an example of tuple unpacking, where Python creates a tuple on the right side and unpacks it into the variables on the left side. You can use this to swap values elegantly. Instead of needing a temporary variable like in many other languages, you can just write x, y equals y. X and Python swaps their values. This works because Python evaluates the entire right side before assigning to the left side. Multiple assignment is also useful when functions return multiple values, since they actually return a tuple that you can unpack. You'll see this pattern frequently in Python code, and it makes many operations more concise and readable than they would be with separate assignment statements. Lists are one of the most fundamental and versatile data structures in Python. A list is an ordered, mutable collection that can contain any mix of data types. You create lists using square brackets, like my list equals bracket 1, 2, 3, 4, 5 close bracket. Lists maintain the order of elements, so the first item you put in stays first unless you explicitly change it. You can access individual elements using indexing with square brackets, where my list bracket 0, close bracket, gives you the first element. Python uses zero-based indexing, which means counting starts at 0 rather than 1. This trips up beginners sometimes, but it's consistent throughout Python and most programming languages. Lists are mutable, meaning you can change them after creation. You can add elements with append, remove elements with remove or pop, insert elements at specific positions with insert, and modify existing elements by assigning to an index. This mutability makes lists perfect for situations where you need a collection that grows, shrinks, or changes as your program runs. List slicing is an incredibly powerful feature that lets you extract portions of a list using a special syntax. The basic form is my list bracket start colon stop close bracket, which gives you elements from a start index up to but not including the stop index. For example, my list bracket 1 colon 4 close bracket gives you elements at positions 1, 2, and 3. You can omit the start to begin from the beginning, or omit the stop to go to the end. So my list bracket colon 3 close bracket gets the first 3 elements, and my list bracket 2 colon close bracket gets everything from index 2 onward. You can also use negative indices to count from the end, where -1 is the last element, -2 is second to last, and so on. There's even a third optional parameter for step, like my list bracket colon 2 close bracket, which gives you every second element. A particularly clever trick is my list bracket colon -1 close bracket, which reverses the list. Slicing creates a new list, so it doesn't modify the original, which is important to remember. Tuples are similar to lists, but with one crucial difference: they're immutable. Once you create a tuple, you cannot change its contents. You create tuples using parentheses, like my tuple equals open paren 1, 2, 3 close paren. Actually, the parentheses are often optional. What really defines a tuple is the comma. You can write my tuple equals 1, 2, 3 without parentheses, and it's still a tuple. This can lead to a quirk. To create a single-element tuple, you need a trailing comma, like my tuple equals open paren 5, close paren. Without that comma, Python just thinks you're using parentheses for grouping. Tuples are useful when you have data that shouldn't change, like coordinates, RGB color values, or database records. They're also slightly more memory efficient than lists and can be used as dictionary keys, which lists cannot because dictionary keys must be immutable. Many Python functions return tuples when they need to return multiple values. Dictionaries are Python's implementation of hash maps or associative arrays, storing data as key-value pairs. You create them using curly braces with colons, separating keys and values, like my dict equals open brace, name colon Alice, age colon 30 close brace. Keys must be immutable types like strings, numbers, or tuples, while values can be anything. You access values using square bracket notation with the key, like my dict bracket name, close bracket gives you Alice. Dictionaries are incredibly fast for lookups because they use hashing under the hood. No matter how large your dictionary gets, looking up a value by its key takes roughly the same amount of time. This makes dictionaries perfect for situations where you need to quickly find data based on some identifier. Starting in Python 3.7, dictionaries maintain insertion order, which wasn't guaranteed in earlier versions. This means when you iterate over a dictionary, items come out in the order you added them. Dictionary methods provide powerful ways to work with key-value data. The get method is safer than direct bracket access because it returns none or a default value if the key doesn't exist, rather than raising an error. The keys method returns all keys. Values returns all values, and items returns key-value pairs. You can check if a key exists using the AND operator, like if name in my dict. The update method merges another dictionary into the current one, and setDefault is a clever method that returns a key's value if it exists or sets, and returns a default if it doesn't. Dictionary comprehensions, which we'll discuss soon, provide a concise way to create dictionaries. Modern Python also has the dictionary union operator, the pipe symbol, that lets you merge dictionaries easily. Understanding these methods makes working with dictionaries much more efficient and helps you write cleaner code. Sets are unordered collections of unique elements, perfect for situations where you need to eliminate duplicates or test membership. You create sets using curly braces with commas, but no colons, like my set equals open brace 1, 2, 3, for close brace. If you try to create a set with duplicate values, Python automatically keeps only one of each. Sets are particularly useful for mathematical set operations. You can find the union of two sets with the pipe operator, the intersection with the ampersand operator, the difference with the minus operator, and the symmetric difference with the caret operator. Sets are implemented using hash tables, which makes membership testing very fast. Checking if an element is in a set is much faster than checking if it's in a list, especially for large collections. This performance characteristic makes sets the right choice when you frequently need to ask, is this item in my collection? You can't access set elements by index, since sets are unordered, but you can iterate over them with a for loop. List comprehensions are a concise and elegant way to create lists based on existing sequences or ranges. Instead of writing a for loop that builds a list by repeatedly calling append, you can express the entire operation in a single line. The basic syntax is bracket expression for item in iterable close bracket. For example, bracket x times 2 for x in range 10 close bracket creates a list of the first 10 even numbers. You can add conditions with an if clause at the end, like bracket x for x in range 20 if x%2 equals 0 close bracket gives you even numbers from 0 to 18. List comprehensions are not just more concise, They're usually faster than equivalent for loops because they're optimized at the interpreter level. They also make your intent clearer to readers who are familiar with the syntax. However, they can become hard to read if you make them too complex, so there's a balance between conciseness and readability. Dictionary comprehensions and set comprehensions work similarly to list comprehensions, but create dictionaries and sets respectively. A dictionary comprehension looks like open brace key expression : value expression for item in iterable close brace. For example, open brace x : x times 2 for x in range 5 close brace creates a dictionary mapping numbers to their squares. Set comprehensions use curly braces without colons, like open brace x times 2 for x in range 10 close brace creates a set of even numbers. These comprehensions are just as useful as list comprehensions and follow the same patterns. You can include conditional logic, iterate over multiple iterables, and nest them, though deep nesting quickly becomes unreadable. Comprehensions represent Pythonic code at its best: concise, readable, and expressive. They let you transform data in ways that would take several lines in other languages, but fit cleanly in one line in Python. The range function generates sequences of numbers and is commonly used in for loops, though it's useful in many other contexts too. Range doesn't actually create a list of numbers. It creates a range object that generates numbers on demand, which is much more memory efficient. The simplest form is range stop, which generates numbers from 0 up to but not including stop. So range 5 gives you 0, 1, 2, 3, 4. You can specify a start with range start, stop, like range 2, 7 gives you 2, 3, 4, 5, 6. There's also an optional step parameter for range start, stop, step, letting you count by 2s, by 10s, or even backwards with negative steps. Range 10, 0, -1 counts down from 10 to 1. Understanding range is crucial because you'll use it constantly in Python, and knowing its features helps you write more efficient loops and avoid creating unnecessary lists in memory. Python's an operator is remarkably versatile and works with all the collection types we've discussed. You can check if an element is in a list, tuple, set, or dictionary with natural syntax, like if 5 in my list. For dictionaries, it checks whether something is a key, not a value. The in operator also works with strings, checking if one string is a substring of another. So hello in hello world returns true. There's also not in, which checks for absence rather than presence. The beauty of in is that it works consistently across different data types, giving you a uniform way to check membership regardless of what kind of collection you're working with. Behind the scenes, the performance characteristics differ. Checking membership in a set or dictionary is very fast regardless of size, while checking in a list requires examining elements one by one and gets slower as the list grows. Knowing these performance differences helps you choose the right data structure for your needs. Conditional statements in Python use if, elif, and else keywords to control program flow based on conditions. The basic structure starts with if followed by a condition and a colon, with a code block indented beneath it. You can chain multiple conditions using elif, which is short for else if, and end with an optional else clause for when none of the conditions are true. Python evaluates conditions from top to bottom and executes only the first block, whose condition is true, then skips the rest. The conditions themselves can be any expression that evaluates to true or false, including comparisons with operators like equals equals, not equals, less than, greater than, less than or equals, and greater than or equals. You can combine multiple conditions with and, or, and not operators to create complex logic. The beauty of Python's conditional syntax is its readability. Code like if temperature greater than 30 : print, it's hot, reads almost like natural English. The for loop in Python iterates over sequences like lists, tuples, strings, or any iterable object. Unlike many languages, where for loops use counter variables and explicit conditions, Python's for loop is really a for each loop. You write for item in collection : and the indented block executes once for each element. When you loop over a list, the loop variable takes on each value in sequence. When you loop over a string, you get each character. When you loop over a dictionary, you get each key. though you can use the items method to get key-value pairs. This design makes Python for loops intuitive and less error-prone than traditional counter-based loops because you're directly working with the data you care about. If you need both the index and the value while looping, the enumerate function provides both, giving you tuples of index value pairs. For loops in Python are the primary way to process collections, and mastering them is essential for writing effective Python code. While loops execute a block of code repeatedly, as long as a condition remains true. The structure is while condition : followed by an indented block. The condition is checked before each iteration, and if it's false, the loop never executes or stops executing. While loops are perfect for situations where you don't know in advance how many iterations you'll need, like reading input until the user types quit, or processing data until you reach the end of a file. You need to be careful with while loops to ensure the condition eventually becomes false. Otherwise, you create an infinite loop that runs forever. Common patterns include incrementing a counter inside the loop or waiting for some external state to change. While loops are less common in Python than for loops, because iterating over collections is such a common task, but they're invaluable when the number of iterations depends on runtime conditions rather than a predetermined sequence. The break statement immediately exits the innermost loop, regardless of the loop's condition. When Python encounters break, it stops executing the loop body and continues with the code after the loop. Break is useful when you're searching for something in a collection and want to stop as soon as you find it, rather than continuing to check remaining elements. It's also common in while true loops, which create infinite loops that you deliberately break out of when a condition is met. The continue statement is related but different. It skips the rest of the current iteration and jumps to the next iteration. When Python encounters continue, it immediately goes back to the loop header without executing any remaining code in the loop body. This is useful for skipping certain elements that you want to ignore. Both break and continue only affect the innermost loop if you have nested loops, which is an important consideration when working with complex loop structures. Functions in Python are defined using the def keyword followed by the function name, parentheses containing any parameters, and a colon. The function body is indented beneath the definition. Functions can accept parameters, which are variables that receive values when the function is called. You can define default values for parameters, making them optional. When you call a function with default parameters, you can omit those arguments and the defaults will be used. Python allows you to call functions using positional arguments, where values are matched to parameters by position, or keyword arguments, where you explicitly specify which parameter gets which value. Keyword arguments make function calls more readable and let you skip optional parameters in the middle of the parameter list. Functions can return values using the return statement, or they can perform actions without returning anything, in which case they implicitly return none. Well-designed functions follow the single responsibility principle, doing one thing and doing it well, which makes code more modular, testable, and reusable. Function arguments in Python have several advanced features that make them incredibly flexible. You can use *args in your parameter list to accept any number of positional arguments. Inside the function, args becomes a tuple containing all the extra positional arguments. Similarly, *quargs accepts any number of keyword arguments, making quargs a dictionary of argument names and values. These features let you create functions that work with varying numbers of arguments, which is useful for wrapper functions and APIs that need flexibility. Python also supports keyword-only arguments, which must be specified by name when calling the function. You create these by putting them after an asterisk or after *args in the parameter list. This forces callers to use descriptive names, making the code more readable. Understanding these argument types helps you design clear function interfaces and use Python's standard library functions more effectively, since many of them use these features. Scope in Python determines where variables are accessible in your code. There are 4 scope levels: local scope inside functions, enclosing scope in outer functions when you have nested functions, global scope at the module level, and built-in scope for Python's built-in names. Python follows the LEGB rule when looking up variables. It checks local, then enclosing, then global, then built-in scopes until it finds the name. When you assign to a variable inside a function, Python creates a local variable by default, even if a variable with the same name exists in an outer scope. If you want to modify a global variable from inside a function, you need to use the global keyword to declare that you're referring to the global variable. Similarly, the non-local keyword lets you modify variables from an enclosing function scope. Understanding scope is crucial for avoiding bugs where variables have unexpected values or where you accidentally shadow global variables with local ones. Lambda functions, also called anonymous functions, are small functions defined without the def keyword. You create them using the lambda keyword followed by parameters, a colon, and a single expression. The syntax is lambda parameters colon expression. For example, lambda x colon x times 2 creates a function that doubles its input. Lambda functions automatically return the value of their expression. You don't use a return statement. They're limited to a single expression, so you can't include statements like assignments or multiple operations. Lambda functions are useful as quick, throwaway functions, especially when you're passing a simple function as an argument to another function. They're commonly used with functions like map, filter, and sorted that accept functions as parameters. While lambda functions are convenient, you should use regular def functions when the logic becomes complex, as lambda functions can hurt readability if overused. The key is recognizing when a lambda makes code clearer versus when it makes it more cryptic. The map function applies a function to every item in an iterable and returns an iterator with the results. The syntax is map function comma iterable. For example, map lambda x colon x times 2 comma bracket 1 comma 2 comma 3 close bracket would square each number. Map is functional programming technique that lets you transform collections without explicit loops. The filter function is similar but keeps only items where the function returns true, effectively filtering the collection. Filter lambda x colon x percent 2 equals 0 comma. Some list keeps only even numbers. Both map and filter return iterators rather than lists, so you often need to convert them with the list function if you want a concrete list. While map and filter are useful, Python's list comprehensions often provide a more readable alternative. Comprehensions are generally preferred in modern Python because they're more Pythonic and often clearer in intent, but understanding map and filter is valuable because you'll encounter them in existing code. Recursion is when a function calls itself, and Python supports recursive functions, just like most programming languages. A recursive function needs two key components: a base case that stops the recursion, and a recursive case that calls the function with different arguments, moving toward the base case. Classic examples include calculating factorials or traversing tree structures. While recursion is elegant for problems with recursive structure, Python isn't optimized for deep recursion. Python has a recursion limit, defaultable around 1,000 calls, to prevent infinite recursion from crashing the interpreter. You can check or modify this limit with a sys module, though increasing it too much can cause problems. For many problems that could use recursion, iteration with loops is more efficient in Python and doesn't have depth limits. However, recursion remains valuable for naturally recursive problems, like processing nested data structures, implementing algorithms like quicksort or tree traversal, and when recursive solutions are clearer than iterative ones. Understanding both approaches lets you choose the right tool for each situation. Classes in Python are blueprints for creating objects that bundle data and functionality together. You define a class using the class keyword, followed by the class name and a colon, with the class body indented beneath. By convention, class names use capword style, where each word starts with a capital letter. Inside a class, you define methods, which are functions that belong to the class. The most important method is underscore underscore init underscore underscore, called the initializer or constructor, which runs automatically when you create a new instance of the class. This method typically sets up the initial state of the object by assigning values to instance variables. The first parameter of every instance method is self, which refers to the instance itself. Python passes the instance automatically as the first argument when you call methods, so you don't include it when making the call. Classes let you model real-world entities or abstract concepts, grouping related data and the operations that work on that data into a single cohesive unit. Instance variables store data that's unique to each instance of a class, while class variables are shared among all instances. You create instance variables by assigning to self.variable name inside methods, typically in the init method. Each object gets its own copy of instance variables. Class variables, on the other hand, are defined directly in the class body outside any method. They're useful for data that should be the same across all instances, like configuration values or counters, tracking how many instances exist. When you access a variable through an instance, Python first checks if the instance has that variable, and if not, it looks at the class level. This can lead to subtle bugs if you're not careful. Assigning to an instance variable shadows a class variable with the same name. Understanding the distinction between instance and class variables is crucial for properly organizing data in your classes and avoiding unexpected behavior where changes to one instance affect others. Methods in Python classes come in three main types: instance methods, class methods, and static methods. Instance methods are the most common and operate on individual instances, receiving self as the first parameter. They can access and modify instance variables and call other instance methods. Class methods are marked with the class method decorator and receive the class itself as the first parameter, conventionally named CLS. They can access and modify class variables and are often used as alternative constructors that create instances in different ways. Static methods are marked with its static method and don't receive self or CLS automatically. They're basically regular functions that belong to the class namespace because they're logically related to the class, but they don't need access to instance or class data. Choosing the right type of method helps you organize code logically and signals to other programmers how each method should be used. Inheritance allows you to create new classes based on existing ones, inheriting their attributes and methods. The new class, called a subclass or derived class, can add new functionality or override existing behavior while keeping the functionality it inherits. You specify inheritance by putting the parent class name in parentheses after the subclass name. The subclass automatically gets all methods and attributes from the parent class, called the superclass or base class. You can override methods by defining them again in the subclass with the same name. Inside an overridden method, you can call the parent class version using super, which returns a proxy object that lets you access parent class methods. Inheritance represents an is-a relationship, where the subclass is a more specific type of the parent class. It's a powerful tool for code reuse and organizing hierarchies of related classes, though it should be used thoughtfully since overly deep inheritance hierarchies can make code hard to understand. Python supports multiple inheritance, where a class can inherit from multiple parent classes. You specify multiple parents by separating them with commas in the class definition. When you call a method on an instance, Python searches for that method using the method resolution order, or MRO, which determines which parent class to check first when multiple parents might have the same method. Python uses an algorithm called C3 linearization to compute the MRO, which ensures a consistent and predictable order. You can view a class's MRO using the _mro___ attribute, or the mro method. Multiple inheritance is powerful but can be complex, especially when parents have conflicting method names. Many Python programmers prefer composition over multiple inheritance, where a class contains instances of other classes rather than inheriting from them. However, multiple inheritance is used effectively in Python, particularly with mixins, which are small classes designed to add specific functionality when mixed into other classes. Magic methods, also called dunder methods because they have double underscores before and after their names, let you define how your objects behave with Python's built-in operations. The init method is one magic method, but there are many others. The __str___ method defines how your object appears when converted to a string, which is what print uses. The __, representing ___ method provides a more detailed string representation useful for debugging. The __len___ method lets you use the len function on your objects. Comparison magic methods like __eq__ for equality and __lt__ for less than let you use comparison operators with your objects. Arithmetic magic methods like underscore underscore add underscore underscore and underscore underscore mul underscore underscore let you use plus and times operators. By implementing these methods, you make your custom objects behave like built-in types, which makes them more intuitive to use. Encapsulation is the principle of bundling data and methods that work on that data within a class, while restricting direct access to some components. Python doesn't have true private variables like some languages, but it has conventions. A single leading underscore signals that a variable or method is intended for internal use and shouldn't be accessed from outside the class. This is just a convention that Python doesn't enforce, relying on programmers to respect it. A double leading underscore triggers name mangling, where Python changes the name to include the class name, making it harder to access accidentally. However, this still isn't truly private, since you can access mangled names if you know the pattern. The Python philosophy is that programmers are consenting adults who can be trusted not to access internal implementation details. This approach keeps the language simple while still allowing you to signal your intent about what's public interface versus implementation detail. Properties in Python provide a way to add getter, setter, and deleter logic to attributes while keeping attribute-style access syntax. Instead of calling methods with parentheses, users can access properties like regular attributes. You create properties using the addProperty decorator on a method. That method becomes the getter, running whenever someone accesses the attribute. You can add a setter with a attribute name.setter and a deleter with a attribute name.deleter. Properties are useful when you want to add validation, computation, or side effects to attribute access without breaking existing code that accesses attributes directly. For example, you might have a temperature property that validates that the value isn't below absolute zero, or an age property that computes the age from a stored birth date. Properties let you start with simple attributes and add logic later without changing how the class is used, which makes your classes more maintainable and your interface more stable. Class composition is an alternative to inheritance, where one class contains instances of other classes as attributes. Instead of an as-a relationship like inheritance, composition represents a has-a relationship. A car has an engine rather than a car is an engine. Composition is often more flexible than inheritance because you can change behaviors at runtime by swapping out the contained objects, and you avoid the complexity of inheritance hierarchies. The composition approach is favored in many modern software design patterns and is often summarized in the principle favor composition over inheritance. In Python, composition is straightforward. You simply create instance variables that hold instances of other classes. The containing class then delegates operations to its component objects. This approach keeps classes focused and loosely coupled, making code easier to test and modify. When designing classes, it's worth asking whether inheritance truly models an as-a relationship or whether composition with a has-a relationship would be clearer and more flexible. The underscore underscore name underscore underscore variable is a special variable in Python modules that tells you whether a Python file is being run directly or being imported. When you run a Python file directly, Python sets underscore underscore name underscore underscore to the string underscore underscore main underscore underscore. When the file is imported as a module, underscore underscore name underscore underscore is set to the module's name instead. This lets you write code that only runs when the file is executed directly, not when it's imported. The common pattern is to put if underscore underscore name underscore underscore equals underscore underscore main underscore underscore colon at the bottom of your file, with code beneath it that runs tests or demonstrations. This pattern makes your modules reusable because other programs can import your functions and classes without triggering test code or example usage. It's a simple but powerful technique that you'll see in virtually every Python module that can be both imported and run directly. Modules in Python are files containing Python code that you can import and reuse in other programs. Any Python file can be a module, and the file name without the .py extension becomes the module name. You import modules using the import statement, like import math, which gives you access to mathematical functions. After importing, you access the module's contents using dot notation, like math.sqrt, to call the square root function. Python searches for modules in several locations. First, the current directory, then directories listed in the Python path environment variable, then the standard library directories. Understanding modules is fundamental to organizing larger Python programs because they let you split code across multiple files, keeping each file focused and manageable. Modules also provide namespaces, preventing name collisions when different parts of your code use the same names for different things. This modular approach makes code more maintainable and allows multiple programmers to work on different modules simultaneously. Python offers several ways to import from modules, each with different implications for your namespace. The basic import module form requires you to use the module name as a prefix when accessing its contents. You can import specific items with from module import name, which brings those names directly into your namespace without needing the module prefix. You can import everything from a module with from module import asterisk, though this is generally discouraged because it can lead to namespace pollution and makes it unclear where names come from. You can rename imports using as, like import numpy as np or from collections import defaultict as dd, which is useful for long module names or avoiding name conflicts. Each import style has appropriate use cases. Full module imports keep code explicit about where things come from. Specific imports reduce typing for frequently used items, and renaming helps with brevity or resolving conflicts. The Python standard library is extensive and covers a remarkable range of functionality without needing to install anything extra. The datetime module handles dates and times with time zone support. The JSON module parses and generates JSON data. The re module provides regular expressions for pattern matching in text. The OS and pathlib modules work with files and directories across different operating systems. The collections module offers specialized data structures like defaultict, counter, and deque. The itertools module provides tools for working with iterators efficiently. The random module generates random numbers and makes random selections. The urlib and HTTP modules handle web requests. The math and statistics modules provide mathematical functions and statistical calculations. This batteries included philosophy means you can accomplish common tasks using only what comes with Python, making it easy to share code without dependency management complications. Package managers let you install third-party libraries that aren't in the standard library. Pip is Python's standard package installer and comes bundled with modern Python installations. You use pip from the command line to install packages with commands like pip install package name. Pip downloads packages from the Python package index, called PyPI, which hosts hundreds of thousands of packages created by the Python community. You can install specific versions of packages, upgrade existing packages, or uninstall packages you no longer need. The requirements.txt file is a convention for listing all the packages your project depends on, making it easy for others to install everything they need with pip install -our requirements.txt. Understanding pip is essential for Python development because you'll constantly need to install libraries for specific tasks, whether it's web frameworks like Flask and Django, data science libraries like Pandas and Matplotlib, or specialized tools for whatever domain you're working in. Virtual environments solve the problem of different projects needing different versions of the same package. A virtual environment is an isolated Python environment with its own installation directories, separate from your system Python. You create virtual environments using the venv module that comes with Python. The command python-mvenv environment name creates a new virtual environment in a directory. You then activate it, which modifies your command prompt to show you're using that environment and changes which Python interpreter and packages are used. Once activated, packages you install with pip go into that environment rather than system-wide. This isolation prevents conflicts between projects and makes it easy to have project-specific dependencies. When you're done working in a virtual environment, you deactivate it to return to your normal system Python. Virtual environments are considered essential for Python development, and most projects include instructions for creating and activating a virtual environment before installing dependencies. The __ in init__.py file is what makes a directory into a Python package. A package is a collection of modules organized in directories. By placing an underscore underscore init underscore underscore a py file in a directory, you tell Python that the directory should be treated as a package that can be imported. This file can be empty, or it can contain initialization code that runs when the package is imported. It can also define what gets exported when someone imports the package with from package import asterisk. The underscore underscore init underscore underscore file lets you control the public interface of your package and perform any setup needed when the package is first used. Package structure mirrors directory structure, so a package with subpackages creates a hierarchy that helps organize large projects. Understanding packages is crucial for structuring serious Python projects and for using complex third-party libraries that organize their code into logical subpackages. Relative imports let you import modules within the same package using dot notation to specify their location relative to the current module. A single dot means the current package, 2 dots mean the parent package, and you can chain dots to go up multiple levels. For example, from dot import sibling module imports a module in the same package, while from dot dot import something imports from the parent package. Relative imports only work inside packages. They don't work in scripts you run directly. They're useful because they make packages more portable and self-contained. If you rename your package, relative imports still work without modification. However, they can make it less obvious where things come from. So some teams prefer explicit absolute imports. The Python community is somewhat divided on relative versus absolute imports, with PEP8 suggesting absolute imports are preferred but acknowledging relative imports are valid. Understanding both approaches helps you work with different codebases. The dir function is incredibly useful for exploring modules and objects interactively. When you call dir with an object or module, it returns a list of that object's attributes and methods. If you've just imported a new module and aren't sure what it contains, dir module name shows you everything available. Without arguments, djar returns names in the current scope. This function is invaluable when working in the Python interactive interpreter or when exploring unfamiliar code. Combined with help, which provides documentation for objects, and type, which tells you what type something is, dir forms part of the toolkit for understanding code interactively. These introspection capabilities make Python excellent for exploration and learning. You can import a module, use dir to see what's available, use help to read documentation, and immediately start experimenting. This interactive exploration is one of Python's greatest strengths for learning and prototyping. The if underscore underscore name underscore underscore pattern we discussed earlier becomes especially important with modules. When you create a module that others will import, you want to separate the reusable functions and classes from code that demonstrates or tests the module. By putting test code or example usage under if underscore underscore name underscore underscore equals equals underscore underscore main underscore underscore, you ensure that code only runs when someone executes the file directly, not when they import it. This pattern lets the same Python file serve as both an importable module and a runnable script. It's so common that it's almost universal in well-written Python modules. The pattern makes your code more reusable and professional because users can import your utilities without triggering side effects. It also provides a convenient place to put tests, demonstrations, or a command line interface for your module. Python's module search path, accessible as sys.path, determines where Python looks for modules when you import them. This path is a list of directory strings that Python searches in order. It starts with the current directory, includes directories from the Python path environment variable, and includes the standard library location. You can modify sys.path at runtime by appending or inserting directories, which lets you import modules from non-standard locations. This is sometimes necessary for unusual project structures or when working with code that hasn't been properly installed as a package. However, modifying sys.path is generally a last resort because it makes code less portable and harder for others to run. Better solutions usually involve proper package installation, virtual environments, or restructuring your project. Understanding the module search path helps you debug import errors and understand why Python can or cannot find a particular module. When you get module not found error, It means Python searched systapath and didn't find the module in any of those locations. Reading and writing files in Python is straightforward, using the built-in open function. The open function takes a file name and a mode parameter. The mode R opens a file for reading. W opens for writing and creates the file if it doesn't exist or truncates it if it does. A opens for appending to the end without erasing existing content. And X creates a new file but fails if it already exists. You can add a B to any mode for binary mode, which is necessary for non-text files like images or executables. The open function returns a file object that you can read from or write to. For reading, you can use read to get the entire contents as a string, read line to read one line at a time, or read lines to get a list of all lines. For writing, you use the write method with a string. After you're done with a file, you should close it with the close method to free up system resources. File handling is essential for persistent storage, data processing, logging, and countless other programming tasks. Context managers, used with the with statement, are the preferred way to work with files in Python. Instead of manually opening and closing files, you write with open file name as fileObject: and the indented block beneath it. The with statement ensures that the file is properly closed when the block ends, even if an exception occurs. This automatic cleanup prevents resource leaks and makes code cleaner and safer. You don't have to remember to close files or worry about exceptions, preventing cleanup. The with statement works with any object that implements the Context Manager protocol, which includes files, locks, database connections, and many other resources. This pattern is so useful that it's considered the Pythonic way to handle any resource that needs cleanup. When you see within Python code, you know that proper resource management is happening automatically. Learning to use with consistently is a mark of writing mature, professional Python code. Exceptions are Python's way of handling errors and exceptional conditions. When something goes wrong, Python raises an exception, which is an object representing the error. If the exception isn't handled, it propagates up the call stack until it reaches the top level, where it prints a traceback and terminates the program. Common built-in exceptions include value error, when a function receives an argument of the right type, but inappropriate value. Type error when an operation is applied to an object of the wrong type. Key error when you try to access a dictionary key that doesn't exist. Index error when you try to access a list index that's out of range. File not found error when you try to open a non-existent file. And zero division error when you divide by zero. Each exception type conveys specific information about what went wrong. Understanding common exceptions helps you anticipate problems and handle them appropriately rather than letting your program crash. The try except block lets you catch and handle exceptions gracefully instead of letting them crash your program. You put code that might raise an exception in the try block and code to handle specific exceptions in except blocks. You can catch specific exception types with except exception type : or catch multiple types with except open paren exception type 1, exception type 2 close paren : You can also use except without specifying a type to catch any exception, though this is generally discouraged because it can hide bugs. When an exception occurs in the try block, Python immediately jumps to the matching except block, skipping any remaining code in the try block. Exception handling lets you write robust code that deals with error sensibly, whether that means retrying an operation, using a default value, logging the error, or informing the user. Good exception handling is crucial for production code that needs to be reliable and user-friendly. The try except else finally structure provides fine-grained control over exception handling. The else clause runs if the try block completes without raising any exceptions. This is useful for code that should only run if the risky operation succeeded. The finally clause always runs whether an exception occurred or not, making it perfect for cleanup code, like closing files or releasing locks. The pattern is try : for the risky operation, except some exception : for handling specific errors, else : for success-only code, and finally : for cleanup that must always happen. This structure lets you separate different concerns: error-prone operations in try, error handling in except, success path code in else, and mandatory cleanup in finally. While you don't always need all four parts, understanding the complete structure helps you write more precise and maintainable error handling code. Raising exceptions lets you signal errors in your own code. You use the raise statement, followed by an exception instance. You can raise built-in exceptions like raise value error with a message, or create custom exception classes by inheriting from exception or a more specific built-in exception. Custom exceptions help you create meaningful error hierarchies for your code. When you raise an exception, you're essentially saying, I can't handle this situation. Whoever called me needs to deal with it. This is appropriate when a function receives invalid input, encounters an unexpected state, or can't complete its task for any reason. Good exception messages are crucial because they help developers and users understand what went wrong. Include relevant information like what value caused the problem or what conditions weren't met. Raising exceptions is better than returning error codes because exceptions can't be silently ignored, forcing callers to acknowledge and handle errors. Exception chaining with the from keyword preserves context when handling one exception by raising another. When you catch an exception and need to raise a different one, you can write raise new exception from original exception. This creates a chain that preserves the original exception as the cause, which appears in the traceback. Exception chaining helps debugging by showing the complete picture of what went wrong. Python also automatically chains exceptions when one exception occurs while handling another. You can suppress the context with raise new exception from none, which is useful when the original exception isn't relevant to callers. Exception chaining became more sophisticated in Python 3, with the __cause _ and _ context _ attributes storing exception chains. Understanding exception chaining helps you write code that provides clear error information through multiple layers of abstraction. The assert statement checks that a condition is true and raises an assertion error if it's not. You write assert condition or assert condition, message. Assertions are primarily used during development to catch bugs early by verifying assumptions about your code state. They're useful for internal consistency checks that should always be true if your code is working correctly. However, assertions can be globally disabled with the optimize flag when running Python, so you should never use assertions for data validation or catching runtime errors. Use assertions for impossible conditions that indicate bugs, not for expected errors that might occur in normal operation. For example, assert user input is greater than 0 is wrong because invalid input is expected. You should use proper exception handling instead. But assert list length equals expected length in a test is appropriate because it's checking your code's correctness. Understanding when to use assertions versus exceptions is important for writing robust code. Python's exception hierarchy starts with base exception at the root, with exception inheriting from it. You should almost always inherit your custom exceptions from exception rather than base exception. System exit, keyboard interrupt, and generator exit inherit directly from base exception because they're not really errors you want to catch in normal exception handling. Under exception, there's a hierarchy of more specific exceptions. For instance, arithmetic error is a base for zero division error and overflow error. Lookup error is a base for index error and key error. This hierarchy lets you catch groups of related exceptions with a single except clause. When catching exceptions, you should catch the most specific exception that's appropriate. Catching exception catches almost everything, which is usually too broad. The exception hierarchy is designed so you can choose the right level of specificity. Understanding the hierarchy helps you write more precise exception handling that catches what you intend without catching too much. Reading and writing JSON is remarkably simple with Python's JSON module. JSON is a text format for representing data structures, widely used for data exchange, configuration files, and web APIs. The JSON module provides dumps to convert Python objects to JSON strings and loads to parse JSON strings into Python objects. There's also dump and load that work with file objects instead of strings. Python dictionaries map naturally to JSON objects, lists map to JSON arrays, strings to JSON strings, numbers to JSON numbers, true and false to JSON true and false, and none to JSON null. When writing JSON, you can use the indent parameter to make the output readable, like JSON.dumpsData, indent equals 4. The JSON module handles the complexity of formatting and escaping, so you can focus on your data. Being able to easily serialize and deserialize JSON makes Python excellent for working with web APIs and creating configuration files that are both human-readable and machine-parsable. Decorators are a powerful feature that lets you modify or enhance functions and methods without changing their code. A decorator is essentially a function that takes another function as input and returns a modified version. You apply decorators using the @ symbol followed by the decorator name above a function definition. When Python sees this syntax, it automatically passes the function through the decorator. Common use cases include logging function calls, timing execution, checking permissions, caching results, and validating arguments. For example, a timing decorator might record when a function starts and ends, calculate the duration, and log it. Decorators work by wrapping the original function in another function that adds behavior before or after calling the original. This is an example of the decorator design pattern from object-oriented programming. Python's decorator syntax makes this pattern elegant and readable. Understanding decorators is essential for advanced Python programming and for using frameworks like Flask and Django that rely heavily on decorators. Creating your own decorators requires understanding that functions are first-class objects in Python, meaning they can be passed as arguments and returned from other functions. A basic decorator is a function that takes a function, defines a wrapper function inside it that calls the original function, and returns the wrapper. The wrapper function can execute code before the original function, after it, or both. You typically use the functools that wraps decorator on your wrapper function to preserve the original function's metadata, like its name and docstring. Writing decorators that accept arguments requires an additional layer of nesting. You create a function that takes the decorator's arguments and returns the actual decorator function. While this can look complex, the pattern is consistent. Understanding how to create decorators gives you a powerful tool for writing reusable code that adds cross-cutting concerns like logging, caching, or validation without cluttering your business logic. Generators are functions that can pause their execution and resume later, yielding values one at a time rather than computing and returning all values at once. You create generators using the yield keyword instead of return. When you call a generator function, it returns a generator object but doesn't execute the function body yet. Each time you request the next value, the function runs until it hits a yield statement, which produces a value and pauses execution. The next request resumes right where it left off. This lazy evaluation is incredibly memory efficient for large sequences. Instead of creating a list with millions of elements in memory, a generator computes each element only when needed. Generators are perfect for processing large files line by line, generating infinite sequences, or implementing complex iteration logic. The range function in Python 3 is actually a generator-like object that produces numbers on demand rather than creating a list in memory. Generator expressions provide a concise syntax for creating generators, similar to how list comprehensions create lists. The syntax is identical to list comprehensions, except you use parentheses instead of square brackets. For example, open paren x times 2 for x in range 1 million close paren creates a generator that will square numbers on demand, while bracket x times 2 for x in range 1 million close bracket creates a list with all million squared numbers immediately. Generator expressions are useful when you're passing a sequence to a function that processes it iteratively, like sum or max. You save memory by not creating an intermediate list. They're a simple way to get the benefits of generators without writing a full generator function. When you need to iterate over computed values once, generator expressions are often the right choice. They combine the efficiency of generators with the conciseness of comprehensions. Iterators are objects that implement the iterator protocol, which means they have an __iter__ method that returns self, and a __next__ method that returns the next value or raises stop iteration when done. Any object that implements this protocol can be used in for loops, and anywhere else iterables are expected. Lists, tuples, strings, and dictionaries are all iterable because they can create iterators. When you use a for loop, Python calls iter on your object to get an iterator, then repeatedly calls next on that iterator until it raises stop iteration. Understanding iterators helps you understand how Pythons for loops actually work under the hood. You can create custom iterators by implementing these methods in your classes, giving you fine control over how objects are iterated. Iterators are fundamental to Python's design and enable many powerful features like generators, comprehensions, and functional programming patterns. The IterTools module provides a collection of fast, memory-efficient tools for working with iterators. Functions like count generate infinite sequences, cycle repeats a sequence indefinitely, and chain concatenates multiple iterables. Combinatoric functions like permutations, combinations, and product generate mathematical combinations of elements. The GroupB function groups consecutive elements by a key function, useful for processing sorted data. Functions like filterFalse, dropWhile, and takeWhile provide filtering operations. The ILIS function extracts a slice from an iterator without loading everything into memory. These tools let you construct complex iterations by combining simple building blocks. Since they work with iterators, they're extremely memory efficient even with huge datasets. The IterTools module represents functional programming in Python at its finest, allowing you to express complex iteration patterns concisely. Mastering even a few IterTools functions can dramatically improve your code's efficiency and readability. Context managers, which we mentioned with file handling, can be created for your own classes by implementing __enter__ and __exit__ methods. The enter method runs when the with block starts and can return a value that gets assigned to the variable after as. The exit method runs when the block ends, receiving information about any exception that occurred. If exit returns true, it suppresses the exception, otherwise, the exception propagates. This protocol lets you ensure that cleanup code always runs, even if exceptions occur. You can create context managers for database transactions, locks, timing measurements, changing state temporarily, or any situation where you need setup and teardown. The ContextLib module provides utilities for creating context managers more easily, including the Context Manager decorator that lets you write context managers as generators. Understanding context managers helps you write more robust code that properly manages resources and handles errors. The FuncTools module provides higher-order functions and operations on callable objects. The partial function creates new functions with some arguments pre-filled, useful for customizing functions. The LRU_cache decorator caches function results, dramatically speeding up functions that are called repeatedly with the same arguments. The reduce function applies a function cumulatively to sequence items, though it's less commonly used in Python because comprehensions are often clearer. The wraps decorator we mentioned earlier preserves function metadata when writing decorators. The total underscore ordering decorator generates comparison methods when you only define == and one ordering comparison. These utilities solve common problems that come up in functional programming. While you don't need them every day, knowing they exist can save you from reinventing wheels. The FuncTools module represents Python support for functional programming paradigms, alongside its object-oriented features. List comprehensions with multiple for clauses can flatten nested structures or generate combinations. You can write *x, y for x in list 1 for y in list 2 to get all pairs combining elements from both lists. The comprehension evaluates left to right, so the first for clause is the outer loop. You can add conditions at any level, like *x, y for x in list 1 if x greater than 0, for y in list 2 if y not equals x . While powerful, comprehensions with multiple loops can become hard to read. There's a balance between conciseness and clarity. If you find yourself squinting at a comprehension trying to understand it, it's probably too complex and would be clearer as nested for loops. The goal is readable code, and sometimes that means choosing the more verbose option. Understanding the full power of comprehensions gives you options, but good judgment about when to use that power is equally important. Metaclasses are the classes of classes, allowing you to customize class creation itself. While most Python programmers never need to write metaclasses, understanding they exist helps you understand how Python's object model works. Everything in Python is an object, including classes themselves. Classes are instances of metaclasses. The default metaclass is type, which is what creates classes when you use the class keyword. You can create custom metaclasses by inheriting from type and overriding methods like underscore underscore new underscore underscore or underscore underscore init underscore underscore. Metaclasses let you modify class attributes, validate class definitions, register classes automatically, implement singleton patterns, and perform other advanced customizations. They're used internally by some frameworks for tasks like ORM model registration. The famous quote is that if you wonder whether you need metaclasses, you don't. However, knowing they exist demystifies some of Python's magic and helps you understand advanced libraries that use them. NumPy is the fundamental package for numerical computing in Python and forms the foundation of the scientific Python ecosystem. It provides the array object, a multidimensional array that's much more efficient than Python lists for numerical operations. NumPy arrays support vectorized operations, meaning you can perform mathematical operations on entire arrays without writing loops. Operations like adding arrays, multiplying them, or applying functions work element-wise automatically. NumPy includes a vast collection of mathematical functions for linear algebra, statistics, Fourier transforms, and random number generation. The library is implemented in C, making it extremely fast despite being used from Python. Data scientists, engineers, and researchers use NumPy for everything from simple calculations to complex simulations. Understanding NumPy is essential for scientific computing in Python, and it's a prerequisite for libraries like Pandas, SciPy, and TensorFlow that build on its foundation. Pandas is the primary library for data manipulation and analysis in Python. It provides two main data structures: series for one-dimensional labeled data and data frame for two-dimensional tabular data similar to spreadsheets or SQL tables. Pandas excels at reading data from various formats including CSV, Excel, SQL databases, and JSON. Once data is in a data frame, you can filter rows, select columns, group data, perform aggregations, merge datasets, handle missing values, and transform data in countless ways. The syntax is intuitive and powerful, making complex data operations concise. Pandas is built on NumPy, inheriting its performance characteristics while adding higher-level data manipulation tools. It's become the standard tool for data cleaning, preparation, and exploratory analysis in Python. Whether you're analyzing sales data, processing scientific measurements, or preparing data for machine learning, Pandas is likely your starting point. The library has become so central to data work that proficiency with Pandas is often listed in job requirements. Matplotlib is Python's foundational plotting library, providing comprehensive tools for creating static, animated, and interactive visualizations. You can create line plots, scatter plots, bar charts, histograms, pie charts, box plots, and many other visualization types. Matplotlib gives you fine-grained control over every aspect of your plots: colors, line styles, markers, labels, legends, titles, axis limits, and more. The PyPlot module provides a MATLAB-like interface that's familiar to scientific computing users. While Matplotlib's default styles have been criticized as dated, recent versions have improved aesthetics significantly, and you can customize everything or use style sheets for consistent appearance. Matplotlib serves as the foundation for other visualization libraries like Seaborn, which builds on it to provide higher-level statistical visualizations. Understanding Matplotlib basics is valuable even if you primarily use other visualization tools, since they often expose Matplotlib's underlying objects for customization. Django is a high-level web framework that encourages rapid development and clean, pragmatic design. It follows the batteries included philosophy, providing an ORM for database interactions, an admin interface that's generated automatically, authentication and authorization systems, form handling, template engines, and much more out of the box. Django follows the model view template architectural pattern, organizing code into models that represent data, views that handle logic, and templates that define presentation. The framework emphasizes security, helping developers avoid common vulnerabilities like SQL injection, cross-site scripting, and cross-site request forgery. Django's philosophy is that it should be possible to build complete web applications using conventions and built-in features, minimizing the need to make decisions about what third-party packages to use. Major sites like Instagram, Pinterest, and Mozilla use Django. It's particularly well-suited for content-heavy applications, CMS platforms, and applications that need rapid development with strong security. Flask is a micro-web framework that takes a minimalist approach, providing just the essentials and letting you add what you need through extensions. Unlike Django, Flask doesn't include an ORM, admin interface, or form validation by default. Instead, it provides routing, request and response handling, templating with Jinja 2, and a development server. This minimalism makes Flask extremely flexible and easy to learn. You can build anything from tiny APIs to substantial applications by adding extensions for whatever functionality you need. Flask follows WSGI standards and integrates well with other Python packages. Its simplicity makes it popular for microservices, APIs, and prototypes. The learning curve is gentler than Django's, making Flask an excellent choice for beginners learning web development or experienced developers who want control over their stack. Many developers appreciate Flask's explicit approach, where you understand exactly what your application is doing, rather than relying on framework magic. Requests is the de facto standard for making HTTP requests in Python, wrapping the complexity of the underlying URLib with an elegant and intuitive API. Making a GET request is as simple as requests.get with a URL. Post requests use requests.post with data. The library handles URL encoding, form data, JSON serialization, file uploads, cookies, authentication, and SSL verification automatically. Response objects give you easy access to status codes, headers, content as bytes or text, and JSON parsing. Requests makes working with web APIs feel natural and Pythonic. The documentation is excellent, with clear examples for every common use case. While Python includes URLib in the standard library, Requests is so much more pleasant to use that it's become the community standard. The library's creator describes it as HTTP for humans, which perfectly captures its philosophy of making HTTP requests as simple and intuitive as possible. Beautiful Soup is a library for parsing HTML and XML, making it easy to extract data from web pages. It creates a parse tree from page source code that you can navigate, search, and modify. You can find elements by tag name, by CSS class, by ID, or with CSS selectors. Beautiful Soup handles malformed HTML gracefully, which is important since real-world web pages often have markup errors. The library works with different parsers, including Python's built-in HTML.parser and the faster LXML parser. Web scraping with Beautiful Soup typically involves using requests to fetch a page, then using Beautiful Soup to parse it and extract the information you need. This combination is powerful for gathering data from websites that don't offer APIs. Beautiful Soup makes web scraping accessible even to beginners, though you should always respect websites' robots.txt files and terms of service. The library is widely used for data collection, monitoring price changes, gathering research data, and countless other applications. SQL Alchemy is Python's most popular SQL toolkit and object relational mapping library. It provides two main layers, the core, which offers a SQL abstraction for constructing queries programmatically, and the ORM, which lets you work with database tables as Python classes. With the ORM, you define models as classes with attributes representing columns, and SQL Alchemy handles all the SQL generation automatically. You can query databases using Pythonic syntax that SQL Alchemy translates to SQL behind the scenes. The library supports multiple database backends including PostgreSQL, MySQL, SQLite, and Oracle using the same code. This database independence is valuable for applications that might run on different databases in different environments. SQL Alchemy handles complex scenarios like relationships between tables, transactions, connection pooling, and migrations. While it has a steeper learning curve than simpler ORMs, its power and flexibility make it the choice for serious database work in Python. PyTest is the most popular testing framework in Python, offering a more powerful and flexible alternative to the standard Unitest module. PyTest uses plain assert statements rather than special assertion methods, making tests more readable and natural. It provides excellent error reporting that shows you exactly what values caused failures. PyTest's fixture system lets you set up test data and resources that can be reused across tests. You can mark tests to run only under certain conditions, parameterize tests to run with multiple inputs, and organize tests into classes and modules. The framework has a rich plugin ecosystem extending its functionality for various needs. PyTest automatically discovers test files and functions, following naming conventions, so you don't need boilerplate code to set up test suites. Good testing practices are essential for reliable software, and PyTest makes testing so pleasant that developers actually want to write tests. Understanding PyTest is crucial for professional Python development where code quality and correctness matter. Jupyter Notebooks provide an interactive computing environment where you can combine code, visualizations, and narrative text. A notebook consists of cells that can contain code or markdown. You execute code cells individually, seeing results immediately below. This interactive exploration is perfect for data analysis, education, and research. You can create visualizations inline, making it easy to understand your data. Notebooks are shareable, reproducible documents that tell a story with data. They've become the standard tool in data science for exploratory analysis, creating tutorials, and presenting findings. Jupyter supports many programming languages beyond Python through different kernels. While notebooks are excellent for exploration and communication, they're less suitable for production code or version control compared to traditional Python scripts. Understanding when to use notebooks versus regular Python files is important. Notebooks shine for iterative analysis and communication, while scripts are better for automated pipelines and applications. PEP 8 is Python's official style guide, providing conventions for writing readable and consistent code. PEP stands for Python Enhancement Proposal, and PEP 8 is one of the most important. It recommends using 4 spaces for indentation, never tabs. Lines should be at most 79 characters long, though this is increasingly relaxed to 88 or 100 in modern practice. Variable names should be lowercase with underscores, like my_variable. Function names follow the same convention. Class names should use capwords. Constants should be uppercase underscore with underscores. The guide covers white space around operators, blank lines between functions and classes, import organization, and much more. Following PEP 8 makes your code immediately recognizable to other Python programmers and easier to maintain. Tools like Flake 8, Pylint, and Black can automatically check or format your code according to PEP 8. While some rules are flexible, consistency within a project is crucial. Understanding and following PEP 8 is a mark of professional Python programming. Type hints, introduced in Python 3.5, let you annotate variables, function parameters, and return values with their expected types. You write them using colon for variables and parameters and arrow for return types. For example, def greet name :str, close paren arrow str colon. Type hints are optional and don't affect runtime behavior. Python remains dynamically typed and doesn't enforce these hints during execution. However, tools like MYPY can statically analyze your code to catch type errors before runtime. Type hints serve as documentation, making code easier to understand. IDEs use them for better autocomplete and error detection. They're especially valuable in large code bases, where understanding interfaces between components is challenging. The typing module provides complex types like list, dict, optional, union, and more for annotating sophisticated data structures. While not everyone uses type hints, they're becoming increasingly popular in the Python community, especially for libraries and large applications where clarity and maintainability are priorities. List unpacking and extended unpacking provide elegant ways to extract values from sequences. Basic unpacking assigns sequence elements to multiple variables in one line, like x, y, z equals my list. The number of variables must match the sequence length. Extended unpacking, using the asterisk operator, captures multiple elements. You can write first comma asterisk rest equals my list to get the first element and a list of remaining elements. Or asterisk beginning comma last equals my list to get everything except the last element. You can even use first comma asterisk middle comma last to capture both ends and everything between. This feature makes code more expressive and eliminates the need for explicit indexing. Unpacking works with any iterable, not just lists. It's commonly used in for loops with tuples, function return values, and anywhere you need to break apart sequences. Mastering unpacking makes your code more Pythonic and readable. F-strings, introduced in Python 3.6, provide the most readable and convenient way to format strings. You prefix a string with F and can embed expressions in curly braces that are evaluated and inserted. For example, F hello name, you are age years old, evaluates name and age and inserts them. You can include any Python expression, like F, sum is x plus y. F-strings support format specifications, like F, value : 2F for 2 decimal places, or F, number : comma, for 1,000 separators. They're more readable than % formatting or .format method and faster too. F-strings have become the preferred string formatting method in modern Python. They make string construction natural and keep the template and the values close together, improving readability. While older formatting methods still work, F-strings are recommended for new code. Learning F-string formatting specifications lets you control exactly how values are displayed. The walrus operator, introduced in Python 3.8, combines assignment with expressions using : equals. It lets you assign values to variables as part of larger expressions. A common use is in while loops. While line : equals file.readLine makes the assignment and checks if the result is truthy in one step. Another use is in comprehensions. Bracket result for x in data if open paren result : equals expensive function x close paren is not none close bracket computes expensive function once and reuses the result. The walrus operator can make code more concise and efficient by avoiding duplicate computations. However, it can also make code harder to read if overused. The name, walrus operator, comes from its appearance, which vaguely resembles a walrus's face with eyes and tusks. While controversial when introduced, it has found legitimate uses, where it makes code clearer and more efficient. Understanding it helps you read modern Python code, even if you use it sparingly. The enumerate function is essential when you need both indices and values while iterating. Instead of manually maintaining a counter or using range len, you write for index comma value and enumerate my list : Enumerate returns tuples of index value pairs. You can specify a starting index with enumerate my list comma start equals 1 if you want to count from 1. This function makes code cleaner and more Pythonic than traditional counter-based loops. It works with any iterable, not just lists. Enumerate is particularly useful when you need to reference positions while processing elements, like when logging progress or when the position determines how to handle the value. The function is a simple tool that dramatically improves readability compared to manual index management. Along with zip for parallel iteration and reversed for backward iteration, enumerate is part of the essential toolkit for iteration in Python. The zip function pairs up elements from multiple iterables, creating an iterator of tuples. For example, zip names comma ages gives you tuples of corresponding names and ages. This is perfect for processing related sequences in parallel. You can iterate with for name comma age and zip names comma ages : to access paired values. Zip stops when the shortest input iterable is exhausted. If you need to process all elements and want to pad the shorter sequences, itertools to zip_longest is available. You can also use zip to transpose data structures. List zip * matrix transposes a matrix represented as a list of lists. The asterisk unpacks the list so each sublist becomes a separate argument to zip. This technique demonstrates how Python's simple building blocks combine powerfully. Understanding zip and how it relates to unpacking and iteration helps you write elegant code for common data processing tasks. Virtual environments have become even more sophisticated with tools like virtualenv, pipenv, and poetry. While the standard venv module covers basic needs, these tools add features. PyPenv combines pip and virtualenv, managing both packages and virtual environments with a pip file that tracks dependencies more precisely than requirements.txt. Poetry goes further, adding dependency resolution, package publishing, and build management. These tools help with reproducible builds, ensuring that everyone working on a project uses compatible package versions. They distinguish between development dependencies and production dependencies. Understanding these tools is important for professional Python development, where dependency management can become complex. Different projects and teams prefer different tools, so flexibility is valuable. The Python packaging ecosystem continues evolving, with these tools representing modern approaches that go beyond basic pip and venv. Knowing what's available helps you choose appropriate tools for your projects. Python's Global Interpreter Lock, or GIL, is a mechanism that prevents multiple native threads from executing Python code simultaneously. This means Python threads don't provide true parallelism for CPU-bound tasks on multi-core processors. The GIL exists because Python's memory management isn't thread-safe. While this seems limiting, it rarely matters in practice. For I/O-bound tasks like web servers or programs waiting on databases, threading works fine because threads can release the GIL during I/O operations. For CPU-bound parallelism, you use the multiprocessing module, which creates separate processes that each have their own GIL. Each process runs on a different CPU core, achieving true parallelism. Libraries like NumPy also release the GIL during computationally intensive operations. Understanding the GIL helps you choose the right concurrency approach. Threads for I/O-bound tasks, multiprocessing for CPU-bound parallelism. Recent Python versions have improved GIL performance, and there are ongoing discussions about removing or replacing it in future versions. Python's commitment to backward compatibility within major versions means Python 3 code generally works across Python 3 versions, though new features are added regularly. Python 3.6 added f-strings and better dictionaries. Python 3.7 made dictionaries ordered by default. Python 3.8 brought the walrus operator and positional-only parameters. Python 3.9 added dictionary merge operators and improved type hinting. Python 3.10 introduced structural pattern matching with match and case keywords, bringing powerful switch-like functionality to Python. Python 3.11 significantly improved performance and error messages. Python 3.12 added more performance improvements and better error messages. Each version brings refinements and additions while maintaining compatibility. Understanding what features are available in which versions helps you write code that's compatible with your target Python version. The Python community generally moves toward newer versions quickly, but some projects must support older versions. Following Python's development helps you stay current with best practices and modern idioms as the language evolves and improves with each release.